Thank you, Everett, for the introduction, and thank you for the organizers for inviting me to give a talk at this really nice conference. Yeah, so I want to talk about algorithms for number theoretic problems, both from a classical and quantum perspective, and also connected to some contributions from Hendrik. So over the integers, we have as a source of problems from number theory, just like problems of intrinsic interest to number theorists. And one might want to look at Cohen's book for like the main problems. And so these over the integers, one could just talk about compute GCDs. Primality testing is a big one. Then, of course, factoring. And I'll also throw in solving Pell's equation. And so where D is positive and not a square. We have solutions. And then we can sort of look at number fields. And then some more problems. For example, computing discriminants. Or once we can compute discriminants of the number field, we can also compute the ring of integers. So let me refer to the number field as K, and then the ring of integers as OK. We have computing the class group. There's the unit group of units inside the ring of integers. And something maybe slightly discussed slightly less often, the principal ideal problem. Which I will refer to as PIP. And so that in the principal ideal problem, so you have an ideal I inside the ring of integers of your number field. You want to check if it's principal. And if the answer is yes, you want to have a generator. So determining whether it's principal and then also giving a generator if the answer is yes is what I consider solving the principal ideal problem. And then, of course, we have the analogous problems for number fields, for function fields, excuse me. And so here I'm sort of implicitly assuming that we have a finite field underneath, so something like the polynomial ring over FQ. It's like sort of the main thing of interest, and then the function field, of course, and then some finite extension here. And then so then the analogous problems are, again, this time factor polynomials with coefficients in some finite fields. And we can also compute, well, if we view the upstairs things, say, as a function field of a curve, we can talk about computing class groups or divisor class groups, however you want to view it. And then there are, again, also certain unit groups. And François, in his talk yesterday afternoon, he sort of told us what the classical situation is for factoring, and also alluded to the quantum algorithm for factoring, and that's probably maybe the most well-known quantum algorithm, the factoring one. But today I want to talk about sort of what in this landscape in general can be done. And so I'm having a little bit trouble walking after hurting my legs, so I rewrote the overview on this board. So I want to talk about exponential speedups by quantum algorithms. What do I mean by that? It means that there is a quantum algorithm that is exponentially better than the best known classical algorithm for a problem. So of course, right now factoring is on this list. It is possible that someone at some point comes up with a polynomial time factoring algorithm for the classical problem. In that case, this would just get taken on this list, off this list. But right now there is a exponential separation, meaning that none of these problems have polynomial time algorithms, but in fact, all of the problems here have efficient quantum algorithms. And so the two first problems that were solved by Shor in '94, sort of the first examples of quantum algorithms solving number theoretic problems, were for both factoring and discrete log. And it is sort of funny that like both of these happen in the same paper. So basically in one paper, he wiped out all of the hardness assumptions currently made in crypto systems that are used by everyone every day, because they're either using RSA or some sort of ECC to exchange public for public key cryptography. And then here's a list of other things that came after that, which I'm going to talk about a little bit, but I think sort of the feeling was after the results in '94, the question was like, so can quantum algorithms just solve everything efficiently? And it turned out that actually for a really long time, at least in computer science, a really long time, 8 years. So probably if this were number theory, it would have to be at least like for 200 years, no progress was made. But in computer science, it was for 8 years. People didn't really come up with any new problems. And then John Holgren came up with an efficient algorithm for the Pell equation that I have on the board here. And the date is 2002. And so this is, so the motivation for working on this problem is related to Henrik. I don't know if, so in fall 2000, there was this computational semester at MSRI. I was a graduate student at Berkeley at the time, and I sort of remembered that you had to go to the number theory seminar before the MSRI Hill bus came, because otherwise all the seats would be taken. So it was very competitive to get a seat even in the seminar that semester. And Henrik gave a talk at MSRI in August 2000 on the Pell equation, and that's also on solving the Pell equation. And so Holgren went to that talk, so I asked about how this all came about, and didn't really see anything that you could use. But then Sean gave a talk on the hidden subgroup problem, which I'm going to talk about, which is sort of one of the mechanisms that is used in quantum algorithms, and talked to Henrik about potential problems from number theory that one could solve with quantum algorithms. And sort of Francois already mentioned that even in the factoring, you sort of you do some sort of order finding business, and the same in discrete log. And so for Pell's equation, which is really, well, we're not actually going to find the smallest solution. We're going to find log of the smallest solution. We're going to find the regulator here because the smallest solution might be too big. And So we do have a function. It's possible to construct a function whose period is the regulator, and that's really the function that this quantum algorithm for Pell's equation computed. And I think so that was a very fruitful discussion, and it sort of led to really this whole list of results for number fields, because solutions to Pell's equations are units in Q joint square root of D that sort of paved the way for studying more of these unit group questions for higher degree number field. So first, for so when I'm talking about constant degree number field, it just means when I'm looking at the complexity as the algorithm, I'm viewing the degree of the number field as a constant. And so for a while, that was all that could be done. And then in 2014, it was possible to extend that to arbitrary degree number fields. And the problem there, I'll talk a little bit about it, is basically that if you let the degree grow, you're going to get rounding issues, and quantum computers still need a finite length input, so you need to have some so you need to round to a certain precision, and when you do lots of computation, there are lots of things that can go wrong. The function field analog, because of something called the infrastructure in the function field case, doesn't have this problem, and you never have any problems with the arbitrary degree. So that was done by myself and Holger in 2012, and these other results. So I sort of got interested in these problems around 2010, when we worked on like Ray class groups and sort of looked at subfields of Hilbert's class fields. That sort of, as the problem sort of got more number theoretic, I got involved in some of these collaborations. So these are sort of the problems intrinsic to number theorists. And then there's a second group of questions. So other source of computational problems, problems whose hardness is related to the security of some public key crypto system. And so in a public key crypto system, the idea is that everyone can only communicate over a public channel, but you still want to set up a secret, even though you don't have any way to agree on a joint secret in advance. So somehow that has to be able, you have to be able to do that out in the open. And if you look at sort of one of the standard textbooks, Katz-Lindell, that's Jonathan Katz, Introduction to Modern Cryptography, he just sort of says matter of fact that in this public key settings, all the constructions really come from some hard problem from number theory. That they're all, it turns out they all come from something like that. So let me just give some examples. So I'm going to write down the crypto system and what it's based on. And as we saw last summer, I'll mention that in more detail. The hard needs a question mark because there is still a lot of movement in the area. So we have RSA, which where the related problem is factoring. So if you can factor integers, then you can break RSA. Other way around is not clear. Then you have elliptic curve cryptography. that is just, so when people say ECC, they mean the system that works with one curve, takes a point on the curve, you take a multiple, and then you have, once you have the coordinates of the multiple of the point, you can't really recover what the original point was, what the multiple was, excuse me, of the original point. So that, so the problem I'm alluding to, that is the underlying hard problem here, is the elliptic curve discrete log problem. And so these are two classical systems that are widely used, and I want to say almost exclusively used. I don't know if anything else is currently being used. Then we have some new proposals. Either, I'm just listing two problems here, either ring LWE or LWE. LWE stands for learning with errors. It's some lattice problems and problems related to that are sort of some of the hottest contenders for the new standardization. And so one of the underlying problems, I don't want to get too technical here, is the shortest vector problem. But so if for the general problem, learning with errors, it's just in lattices. But when you have underlying ring, you end up with working with what's called an ideal lattice. And we already saw that in a previous talk for the ring of integers. Sort of you can embed an ideal of the ring of integers via the Minkowski embedding into R to the n, and it forms a lattice there, and that's what we refer to as an ideal lattice. So something that comes from an ideal, and so it has some extra structure. So then there are the supersingular curves, supersingular isogeny-based crypto, which has several different instantiation. And I am going to give the example of SIDH. I'm only gonna say what it stands for, supersingular isogeny Diffie-Hellman. So understandable why everyone just refers to it as SIDH. And so the underlying hard problem is here, computing isogenies between supersingular curves when certain torsion information is known. I'll say more about that. And then to throw in one more system that is also based on lattices to sort of showcase what can go wrong is soliloquy, which was originally suggested by GCHQ. And this is based on what will be referred to later on as the Schur generator principal ideal problem. So that is sort of some selection of systems and underlying problems. There are others like Michelle's, for example, which are code-based systems. But today I'm just going to, besides the ones that are already broken by quantum computers, I'm going to just look at some lattice systems and at something with the supersingular curves. And so one question is, how do you think about these quantum algorithms? What can they actually do? What is sort of their power? And if you don't want to start talking about qubits and superpositions and measuring registers and what the algorithm does, sort of one nice algebraic framework in which to understand them is that there is sort of one prototype of problem that in many cases they can solve efficiently, and that's what's called the hidden subgroup problem. So the approach for many quantum algorithms The initial result may not have framed it like that, but for example, discrete log, factoring, also Pell's equation, but there I already have to be a little bit careful because the group gets a little bit big. So is to give a class, often, let me just say reduction. From the problem you want to solve, or like discrete log or factoring to a hidden subgroup problem. And then to the second step is then we refer to that as HSP. And so there are a bunch of different ones, but whichever one you reduce the two in one, you want to show that that has an efficient quantum algorithm. So what is this hidden subgroup problem? It's just defined in terms of maps from a group to a set. So if you have some function f from a group G to a set S, and you want this function to be constant, and take different values on the different cosets of a subgroup. And so we want to find the subgroup. Now, if this a function is so this is a function, you can just query it. You can give it a group element and it spits out some answer. Now, of course, if you're allowed arbitrarily many queries, you can just solve this problem because it'll show you exactly what the subgroup would be. But the idea is that you want to solve this efficiently. So if, just to give an example, if you have a finite group with n elements, you want to do log n queries. And so classically, it's not known that this can be done. And really the hardness of the problem just depends on what this group is. So in particular, if G is a finitely generated abelian group, you can show there is an efficient quantum algorithm. For the hidden subgroup problem for G to NES. And so some of the problems I've listed earlier reduce to the hidden subgroup problem. So discrete log, let's say discrete log in a multiplicative group of a finite field, let's say with p elements. So just to make it simple, you can show how to reduce this to a hidden subgroup problem over ZP minus 1 plus ZP minus 1. And factoring reduces to an HSP over the integers. And so these two examples fall squarely into this hidden subgroup framework that is solvable right away. There are also other ones. So here I listed Pell's equation. And that turns out reduces to a hidden subgroup problem over R. And now there's already like trouble because quantum computers can't really compute with real numbers. They have to truncate. So you may not actually be able to, and if you round or do something, you may have trouble exactly detecting what's going on. Yes?
So when the group is infinite, what are the sort of parameters you need?
Oh, so then you're talking about the index of the group, for example. Yeah. Okay, so this is sort of the framework that was used for a lot of the problems that I'm listing here. So for both, also for number fields and arbitrary degree number fields with some modification. And so I do want to talk about post-quantum cryptography now a little bit. And so just to remind people, it already came up yesterday. So the goal is in post-quantum cryptography is to develop crypto systems that are secure against quantum computers, so for which there is not an efficient quantum algorithm. Yes? Yes?
Can you describe maybe what you do for the unit group? Like what information are you given and starting point?
The starting point is just the number field. So you can give that.
Maybe some polynomial that.
Yeah. So, pardon?
I said I'll give you some polynomial that's irreducible.
Yeah.
You and
Yeah, and sort of the complexity of the problem might just be the multiplication table that you get associated with that. And so you just have as the input is the number field in some form, and the output is supposed to be, well, the units would be too big, but you're mapping them to a lattice with a log map, like in Dirichlet's theorem. And then you give generators for what's called the unit lattice. And
but I guess up to some precision.
correct. And so the idea is that in the algorithm, you can say how many bits of precision you would want, and that determines to what high precision you have to represent everything in that algorithm. Yeah. And so, so we know that it's easy to list what things are bad choices. RSA, elliptic curve cryptography are both not good choices for candidates for post-quantum cryptography, but it's much less clear what good choices would be. And so this is what the NIST competition is about. So the NIST competition, so NIST is the National Institute of Standards in the US, and they sort of say, oh, if you're gonna use RSA or ECC, here are the parameter sizes that you use. And at some point, I think in 2015, they had the NSA started to have this ominous sentence on their webpage. If you haven't upgraded yet to elliptic curve cryptography, don't bother doing it, because we're going to come out with quantum resistant recommendations. So don't do any more updates right now on to other systems. And well, so one could say, well, is this really urgent right now? Because we've seen quantum computers, they're not really up to scale. On the other hand, figuring out what algorithms would be good candidates to replace that might take decades, and changing the infrastructure, if you talk to people who are sort of more knowledgeable about this than me, the conservative estimate, I think, is 20, 30 years until every government computer is changed to the new system. So that means if you think that maybe they can build quantum computers in 5 years, you're already like 40 years behind the curve. So you have to kind of start early. And it is true that sort of Microsoft and Google offer these cloud computing services where you can rent time on a quantum computer, and they're like spending, I don't know if it's billions probably, in sort of developing this technology. So I think unless you can sort of show that these will never ever be built, you sort of can't just completely let it go. And so this is why NIST made this competition for good replacement candidates, came out in 2017. I tried to get David Zhao to give a talk in our seminar. He's one of the people who was on the isogeny-based submission, and he said any date after November 30th is fine, because that was the submission deadline to NIST. And all these submissions were public so that everyone could attack them. So there were 69 submissions. A month later, 8 were already broken, and 22 were broken by the end of 2018, so within a year. So they have various rounds where they advance a subset to the next round that looked like the best candidate. 26 made it to the second round in 2019. In round 3, they came up with 7 finalists and 8 alternates. There were lattice-based systems, code-based system, and 1 super singular isogeny still made it to that round. It was one of the alternates. And then the most recent progress was that in July of 2022, July 5th, so they have 4 finalists or 4 candidates selected for standardizations. And 4 more to be studied. And well, I will talk about this in a little bit more detail later, but on July 30th, on the preprint server, there was a paper posted that broke SIDH and broke all the challenges that had been posted. So for some of these systems, they give you like cryptographic size problems and say, this should be hard, and then a bunch of people try and break them. And so all of these were broken on July 30th and have since been, and so SIDH has since been removed from this competition, and they have some sort of sentence, the SIDH development team acknowledges that the system is insecure and should not be used, or something like that. That's like on the official website. And so that means there is sort of a lot of movement here, and a lot of, and this is kind of not what we want to see. I mean, with factoring, this has been studied for so many, for such a long time. One can sort of be maybe confident that if some classical algorithm to factor numbers that is efficient would exist, maybe they would have been found by now. But sort of some of these systems rely on problems that have only been proposed in the last 10 years. So there it's much less, and it's sort of not mainstream problems that number theorists are interested anyway, but that are now only being studied because they're the security assumption for the system. And so there it's much less clear how much attention they have really received. And whether the fact that something hasn't been broken means that nobody has bothered to look at it, or whether it's really a hard system. It's very hard to tell, and I certainly can't say which one it is. And so I do want to say, so in general, it looks like the lattice-based systems are in the lead right now in terms of what looks like a good alternative. I think I must have. But even there, you have to be careful because sort of one of the reasons that lattice problems weren't used to begin with is that they are slower. And so in order to make things more efficient, you might want to get around some of these problems with the speed. And so let me just state, just sort of for concreteness. So I will talk about some lattice-based problems and then mention what happened to SIDH. And so the prototype would be the shortest vector problem. Let me just mention this because it's nice to state. So here the problem is just you have, let's say, we have a full lattice. Let's say we have m vectors in R to the m, generating some lattice L. So let's make them a basis here. And then the goal is to compute the shortest non-zero vector and so this is, of course, one approach would be to like run LLL on the basis and see what you get, and you can show that you're getting within a range of the shortest vector, but it's up to an exponential factor. So it would be possible to base. It is possible to base cryptosystems directly on the shortest vector problem. So, and I just wanted to say that is not what the construction that LWE uses. So I'm not claiming it applies to that. But so if you want to make things more efficient, you could just sort of say, well, if the systems based on the shortest vector problems are really inefficient, I'll just make some extra assumptions that makes the system faster. So one thing one could do is, I want more structure. So problem refers to this problem. So let's first restrict the lattices that we're using. So let's say it's really an embedded ideal via the Minkowski embedding. That's still pretty slow, but now let me call the ideal I. So L is like, sigma is my Minkowski embedding. It's like sigma of I. Well, what else could I do? I could ask that the ideal be principal. And Well, okay, now I is principal, but what if the generator is really big and I can't even write it down? So let me make one more assumption, namely that there is a short generator. So I can, if I have a generator, I can multiply it by a unit in my ring and make it small. So we're working here with some ideal in some number field. And this is what it's referred to as the short generator principal ideal problem. We have an ideal I that's principal and it has a short generator. I'm just already going to abbreviate principal ideal problem as PIP. And then this gets the catchy name SGPIP to not, I know it sounds, it's pretty awful, but it for the talk it's writing down short generator principal ideal problem one more times. So basically the assumption here is that the short generator principal ideal problem must be hard. And that is what was done in the system that is called soliloquy. And then there's also a fully homomorphic encryption scheme by Smart and Papoudaran. And there's also some system with multilinear maps that was based on the hardness on this short generator principal ideal problem. The only problem with that is unfortunately no longer a hard problem for a quantum computer. So now there were too many specializations made so that the final result actually was something that could be attacked. And so, see. So the short generator principal ideal problem can be solved in polynomial time with the quantum algorithm. And so how does that work? So what does the algorithm for the short generator principal ideal problem do? So it has 3 steps, 2 are quantum and 1 is classical. So you're going to compute the unit group. And I'm going to take the log embedding right away. So sort of make things reasonable size. So that means, so you have some, I don't know, okay, I'm going to attempt to draw a lattice, probably later I'm going to have to do some addition. It's probably, okay, I'll do my best. So you have like a unit lattice, so log OK star, it sits inside R to the S plus T minus 1, where S is the number of real embeddings and T is the number of complex conjugate pairs that your number field has. And so the first thing is you find the unit group as a lattice. Then the second step is, because this thing is a principal ideal, and there's sort of a standard way from solving the unit group, computing the unit group to then solve the principal ideal problem. So you can use the techniques in one to solve the principal ideal problem in this field. So that means since you have an ideal I that's principal, so that's the work of Bias and Song, and this is the work of myself that I had mentioned earlier, Sean Holgren, Fang Song, and Alexei Kitayev. This is work. This was done by Bias and Song. So that means now you have some generator beta of this ideal that whose embedding gives you your ideal lattice that you have. And so now I'm just going to take beta and apply log to it. And it's not a unit, so it's going to sit somewhere else. And so maybe it's up here somewhere. So maybe my beta is up here and it's really big. But now I know if I want to make it small, I just need to multiply it by a unit. And what I want to do is I find the closest unit. I'll multiply it by just the inverse. And then I get something down here like that. So that means, so the problem, so now we have some point beta here in this real space, r to the s plus t minus 1. And we're finding the closest point in the unit lattice to it. And that's called, it's sometimes referred to as bounded distance decoding. And in this particular setup, there is a classical algorithm that was found by Piker, Dukas, and some other people. So for bounded distance decoding, I'm just going to refer to it as BDD in this unit lattice. And so if this is my epsilon, my closest unit, then I want to shift by that and get the so let me just say alpha, which is beta times epsilon inverse. So where epsilon and I guess I'm not actually drawing beta, I'm drawing log, everything is log. And that's why it's just so I'm just doing, so here, I'm getting some point down here that, so I'm getting some short vector somewhere down here that gives me log alpha is log beta, which is the large point minus the close point. Yes, let me just make it consistent here that everything is uppercase. So I'm just writing capital log because it's like still this tuple. So that means sort of in this picture, I can move log beta, I subtract log epsilon from it, and then I get something much smaller. And that finds the short generator and breaks the system. And it was a little bit of a surprise because since Shor had come up with his algorithm for discrete log and factoring, people had always asked, well, but how about lattice problems? Quantum algorithms can't do anything for lattice problems. And it's true that these kind of systems still, nobody has any idea how to attack them either classically or in a quantum way. But if you do too many specializations in your system, you may end up with something that is vulnerable. And so this is sort of, I think the paper that was published by the people who had designed this was, the title was Soliloquy, a Cautionary Tale, sort of that you still have to sort of at least consider the possibility that there is a quantum algorithm for a problem. So just to say what happens with this unit group, it can be a reduced to hidden subgroup problem over R to the N, where N can now be anything. And the problem there is that we really have to relax our definition of what the hidden subgroup problem is, because we can't even represent points because we have only some amount of precision. So that means we sort of, first of all, have to like put little Gaussians around the point because we can only compute the points up to some precision. We also we really have to have more like a fall off condition rather than demanding that this function f that hit this group is really distinct on cosets. You have to some sort of relaxed version of that. And there's also a problem because these lattices don't have integer coefficients. They are lattices with real entries, and there isn't a standard basis. And in this hidden subgroup problem, if you want to work with lattices, they must have unique representatives. So that means you kind of have to, so you can't just pick a canonical basis to represent your lattices. Instead, you're sort of representing a given lattice as a superposition of lattice points. And then this superposition also puts like a little superposition around each lattice points because you can't get the accuracy that you like hit the point on the spot. So you get some sort of two Gaussians lying on top of each other, and then you have to show that all the estimates with the precision that someone had already asked about, that this is all going to work out. And that's sort of, you can control the output precision to which you get the units from, like you can predict how much input precision you need for these elements that you put in. So that is all I wanted to say about lattices. And then since it was so recent, I wanted to at least mention what happened with the system based on isogenies. So let me remove the lattices. So this is for supersingular elliptic curves. Sarah, in her talk yesterday, had already talked about the isogeny graph, that the endomorphism rings are non-commutative. And so I want to just mention the system SIDH and what led to its break. So what is SIDH? So let's take a supersingular elliptic curve. So I want to take one in characteristic P. The nice thing is with supersingular elliptic curves, they always have models defined over FP squared. And here P in the system that was submitted to NIST, and that's for simplicity the one, even though the break works more generally. My prime is of the form 2 to the A, 3 to the B minus 1. And I want to have 2 to the A roughly the same size as 3 to the B. And I am going to just assume for simplicity that 2 to the A minus 3 to the B is bigger than 0. You can get around that too, but I don't want to make things more complicated. And so then let's take an elliptic curve. I think you can take, I think this is the one that was used in the NIST submission. The starting curve is known. The number of points over FP squared is just the 2 to the A, 3 to the B torsion. And so the number of points over FP squared is P2 plus 1 squared. And so then I have fp squared rational 2 to the a torsion and 3 to the b torsion. So I'm going to just fix a basis. PA, QA is a basis for the 2 to the a torsion. And QA, PB and QB is a basis for the 3 to the b torsion. And if you haven't seen this, this is a key exchange. So that means two parties communicate, and computer scientists, to be like very engaging, rather than calling the parties A and B, which is what mathematicians would do, they call them Alice and Bob. And then the eavesdropper is called Eve and all of these things. I don't know if it, so that means everything is always in terms of Alice and Bob. So Alice chooses a secret isogeny for what we really want. So we have the starting curve E. And so Alice chooses a secret isogeny to some curve EA. So, and I can specify the isogeny by its subgroup. And this is going to be a T to the A isogeny. Cyclic. So, and she sends the J invariant to Bob. And there's going to be something else. So Bob does the same thing. That's why the points for the 2 torsion have subscript A, and the 3 torsion have subscript B. And now the joint secret, and this is why it has this name for Diffie, why Diffie-Hellman shows up. If you're familiar with the Diffie-Hellman, the regular Diffie-Hellman key exchange, where you sort of, one person knows the secret A, other person knows only the what it looks like raised to the exponent, but sort of together they can do it. And so the secret curve is supposed to be this curve where you mod out both by the subgroup A and the subgroup B. So that means Alice basically chooses the secret subgroup A that determines phi A. Same with Bob for B. And the idea is that they then just have this joint secret. And if that was always needed, this wouldn't be broken. But in order to compute this quotient of E by the subgroup A and B, you need more information. It's not enough to just know what, it's not enough to know A and E mod B to compute what this quotient is. You also need to know what the map does on certain torsion groups, and that was exactly the downfall. So that means Bob also has to reveal. He has to tell her what phi B is evaluated at the 2 torsion. And vice versa. And So as like my final point, so now you could, and I think at least some people I talked to, and it was in several papers, they always say, oh, nobody knows how to exploit the torsion information that has to be given, but it makes people very uncomfortable. Drew is laughing. Yeah, so this was, and for like a long time, it seems like, well, you have a secret 3 to the B isogeny and you tell people how it evaluates on some 2-power torsion. What's the big deal? Well, the big deal is that in this break, which is now 3 papers, separate papers, one by Kastrick de Crew, one by Mino, Martindale, and some others, and one by Robert, they were able to package this original isogeny, like let's say we want to attack Bob's secret, they were able to package this 3 to the B isogeny in an isogeny between a product of 2 curves that ends up being a 2 to the A, 2 to the A isogeny. So now you're going up in dimension, but now your isogeny suddenly has a degree that's divisible by a power of 2 only, and you have all this torsion information about this isogeny because it's constructed from the original one. So the new one turns out to be computable with this torsion point information that was given, and from this isogeny between the product of the elliptic curves, you then can also recover the original isogeny, and that is sort of the ingenious thing that happened there, that we went to higher dimension. We got something of a different degree. I won't be able to go into details here, so I'm just going to stop at this point. Thank you very much for your attention.